Okay, we're back. Let's continue the journey towards functional programming with anonymous functions. I'm Daniel. Let's get right into this. All right, so in the IDE, in the part 3 functional programming, let's create a new Scala application. Let's call this anonymous functions. Of course, it's an object, and OK, and then extends app. Let's switch to presentation mode. Alright, so you now know about function types. Now the problem is that instantiating a function is still very much tied to the object-oriented way. So if I define a value doubler, which doubles an int, for example, I would need to create a new function 1 with int and then override def apply with an x, which is an int, and then return x times 2. So this is basically the still object-oriented way of defining an anonymous function and instantiating it on the spot. Now, in Scala, the way that we do that is by just deleting all this crap and just say x int arrow x times 2. So this is basically the exact equivalent expression. So what this does, it instantiates a new function 1 with the override def apply, which takes an x, which is an int, and returns x times 2. This is syntactic sugar for all that crap, and it's called an anonymous function, or a lambda. Now, the name lambda comes from the term lambda calculus, which is the mathematical representation of functional programming. This was formalized by Alonzo Church sometime in the 1930s, so quite a long time ago, roughly at the same time as Alan Turing formalized the computing machines that we use today. But now, in just an abuse of terminology, so to speak, this in our context will be called a lambda. So we will equate anonymous function with a lambda. Now, some syntax rules. So, this lambda thing is a value, which is basically an instance of function 1. Now, what is a type of doubler? Well, it's the type int arrow int. So we can actually declare it as such. So we can say int arrow int, and then equals this guy. Okay. Now, given the fact that I've declared doubler to be an int arrow int, I can actually remove this type and let it be matched by the compiler, just for a shorthand of notation. So if the compiler already knows that this value should be an int arrow int, then it will assume that the expression here will match its types. So x will be an int, and the return value is going to be x times 2, and all the types will match. So the compiler will help you get shorter code. So it will either do that, or it will help you with type inference. So again, if I omit the type, then the compiler will not know what kind of expression this will be in. So you need to specify the correct types here. All right. Now, syntax rules of what happens if you have multiple parameters in a lambda. Let's say we have a val called adder, which is a function that adds 2 numbers. So in that case, we'll have a int and b int arrow a plus b. If I do want to supply the type for this function, I must put in the arguments in between parentheses. So I'm going to say int in between parentheses and then arrow int. Notice in the previous case, I wouldn't need to do that. So I could just simply say int arrow int. Right? But if you have multiple parameters, you have to put them in between parentheses. Cool. Now what happens if you don't have any parameters? So let's say we have a value which says just do something. Then the syntax for a no param lambda is parentheses parentheses arrow and the value that I want to return, say 3. All right, so parentheses arrow 3 is a no parameter lambda that just returns the value 3, and the type for that is parentheses arrow int. Now, I want you to pay very close attention to something. So if I print line just do something versus print lining just do something parentheses, what do you think will happen? Well, let's go ahead and find out. Let's right-click and run. So the first print line prints this guy, which clearly is an instance of something. So it basically prints the function itself. And the just do something called actually prints the value returned by that function. Now, you've probably gotten used to this style of calling methods, but when it comes to lambdas, you must call them with parentheses. So be very careful. This is the function itself, and this is the actual call. Careful. Now, another way of writing lambdas is to use curly braces. This is commonly used syntax and style in practice. So for example, if I declare a val, let's say string to int, this is a common example. And in practice, we often use curly braces, and at the level of the open curly brace, we say string, which is a string, arrow, and right below, we write the implementation. So this is common style. It's not always loved, but this style is sometimes used. All right? All right, let's fill in the pile of syntactic sugar with more syntactic sugar. Watch what I'm writing. Let's say I have a val called nice incrementer, which is a function of type int arrow int, which just increments the parameter. And normally I would write something like x int arrow x plus 1. All right, but a shorter way to write this is, watch this, underscore plus 1. This is equivalent to x arrow x plus 1 to further shorthand the notation. If, for example, I have a 2-parameter function, let's call this nice adder, which is of type int arrow int, instead of saying ab arrow a plus b, we could just simply say underscore plus underscore, where each underscore is a different parameter. So this is equivalent to ab arrow a plus b. Each underscore stands for a different parameter. This notation is extremely useful in practice when you want to chain higher order function calls. But please note that the underscore notation is extremely contextual. If you miss the type, the compiler won't know what each underscore means. So if I delete this type, if I delete this guy, the compiler won't know which underscore means what, and not even how many parameters this guy has. So the compiler has to be 100% sure of the function definitions so that it can safely replace each underscore with each parameter of the proper type. All right, now let's practice what we've learned. So I want you to do a couple of exercises. First, I want you to go to my list, and I want you to replace all function x calls with lambdas. Okay? Second exercise, I want you to define or rewrite the special adder that we wrote in the previous video, the curried one, as an anonymous function. So 2 very simple exercises. Pause the video, work through them, and I'll get back with solutions in just a couple of seconds. All right, first exercise, we switch to my list, and let's kill all these function x calls. So first function 1 call just multiplied an element by 2. So instead of this guy, I'm just going to say lm arrow lm times 2. And that is it. This guy, new function 1, which says element mod 2 is equal to 0. So this is our little predicate. So I'm going to say lm arrow lm mod 2 equal 0. Now, with a flat map, this function 1, from each element, it returns a new cons. So basically, we have an element of type int, and from this element, I create a new cons. And let's clean up this code. Now, if you want an even shorter notation, we could simply say underscore times 2, and underscore mod 2 is equal to 0. But the underscore notation doesn't work for this lambda because we use the element 2 times in the implementation. And as we saw earlier, each underscore stands for a different parameter, so basically you can't use an underscore multiple times. Now, switching back to anonymous functions, let's rewrite the special adder as an anonymous function. This is very simple to write, and when I write it, it will seem very obvious, but it's sometimes hard to think about this. So I'm going to define it right now. I'm going to call this super add, and this will be xint arrow, and this will return another function, yint arrow x plus y. So this is the lambda version of the curried function that we wrote earlier. If you remember, we had all these nested new function 1 with overrides in place. So this is a much more elegant and shorter way to write it. Of course, it works the same way. So if I had super add called with arguments 3 and then with the argument 4, this would work the same way and it would print the number 7. We're going to discuss curried functions very shortly, but for now, these are the solutions to these two very simple exercises. All right, recap time. So our problem was that instead of passing anonymous function x instances every time, which is one, cumbersome and very hard to nest and still object-oriented, we can use lambdas. Now, the anatomy of a lambda looks like this. Parameters, in which each parameter has a name and a type. Then the implementation, which is a single expression. The return type is always inferred, and parentheses are mandatory for more than one parameter, as we've seen in the code. So this is heavy syntactic sugar for instantiating anonymous function x types, but we've also seen further sugar with underscores. Alright, so now you've learned lambdas, which are foundational to functional programming. I'm Daniel. There's more coming in the next video.